Good morning once again, dear colleagues and friends, and thank you for joining Innovation Days webinar today. We are on schedule to continue with the second session of webinar, which is dedicated to the next step of alternative fuels, the new fuels and the outlook in mid-term and in the long term. We will have presentations from Hydrogen Europe and from our partner Polski Rejestr Statków. After that, we'll have a case study from Port of Tallinn dedicated on implementation of LNG and onshore power supply. And we will conclude with Varsila's summary and outlook for the future fuels and what is the best one, what is the one which will solve it all. Will it be such a fuel, or will we have a mixture of all these current green fuels? So with that said, I would like to continue further with the next presentation from Mr. Grzegorz Pawelec from Hydrogen Europe to give us information on the organization, some of the supply chains and conditions for the use of hydrogen fuel in the transport sector. Grzegorz, if you can hear us, the stage is yours. Please do your presentation.
Yes, I can hear you. Hello, good morning. Thank you for inviting me. I'll share my screen in a second. I hope you can see it. So indeed, I will talk a little about the hydrogen technologies and the potential application in the maritime sector. I would like to first start with a couple of words about the organization I represent, Hydrogen Europe. We are an industry association representing the hydrogen industry in Europe, but not, let's say, not the whole hydrogen industry, only the clean hydrogen industry part of it. So we focus mostly on renewable hydrogen, low carbon hydrogen, and we see it basically as a potential vector to decarbonize the whole society and the European economy. Obviously, the maritime sector is a part of that. But we are not just any hydrogen association. We have let's say, a second part of what we do, which is we are partners together with the European Commission in the Fuel Cell and Hydrogen Joint Undertaking, which is a program to fund R&D activities in the clean hydrogen sector, focusing on energy and transport sector, and maritime is part of that. So far, we have funded more than 1 billion euro worth of projects in the previous 14 years. And this is important also to understand kind of why we have did this analysis that I will present in the next slides. Because this was let's say, the beginning of this analysis was to inform our research and innovation agenda of this particular funding program. So we wanted to find out for ourselves also if hydrogen makes sense in the maritime sector at all, and if it does, which sectors or which applications should we focus on when we discuss the hydrogen application in the sector. So here it was what we covered in the analysis, and because, as I mentioned, this was aimed at informing our own strategic research and innovation agenda, we did not focus on batteries, we did not focus on biofuels. This is not to say that those are not viable options for the maritime sector, but it just was out of scope of our analysis. So what we did look at, so we focused on renewable hydrogen as a starting point, and then we obviously looked at various ways you can use that hydrogen in the shipping sector. And you can obviously use it either in compressed form or liquefied form directly, or you can use hydrogen carriers like liquid organic hydrogen carriers. There are also other like metal hydrides, for example, but we focused on the LOHC. Then, of course, you can synthesize the hydrogen with nitrogen captured from the air, and you can produce green ammonia or synthetic ammonia or e-ammonia, whatever name you want to call it, and then use that ammonia as a fuel for the ship. Or you can synthesize the renewable hydrogen with CO2 to produce synthetic methane, LNG, synthetic methanol, or even synthetic diesel. And that CO2 is from a sustainable source. And then obviously those, let's say, ways of doing it are perfectly fine sustainable solutions. There is nothing wrong with those options. And then at the last part, you have various ways of reconverting that whatever fuel you choose back into energy, and then you can obviously burn it in an internal combustion engine, as it's mostly done today. Or you can use a fuel cell as your reconverter. It's either low temperature fuel cell or high temperature fuel cell. The low temperature, if you would like to use it with some of those complex fuels like ammonia or the synthetic fuels, would require obviously some reforming on board of a ship, either an ammonia cracker, for example, which would add, let's say, another dimension to the amount of storage that you need on board of a ship to make that fuel work for you. For the high temperature fuel cells, you don't need that, but those cost a bit more. So we took all of those into account. But what's important, what you can already see on this graph, is that if you try to, let's say, find all the possible permutations and combinations of those various options, you see that only for hydrogen there is a couple of dozens possibilities that you can do produce a sustainable fuel with renewable hydrogen. And then if you also look at, let's say, maybe low carbon hydrogen sources from natural gas with CCS and maybe from biofuels, you see that there are just so many options that at this point this is becoming a bit of a disadvantage because, I mean, it holds back a lot of investment in the field. The ports are not willing to invest in storage or bunkering infrastructure for fuels that they don't know is going to be the one that is the fuel of choice in the future. The ship owners are not willing to invest in new ships using either one of those options because, I mean, if the ships are expected to last for 20, 30 years, you want to invest in an asset that you are certain that in 10 years' time will be able to find the fuel that it needs. So this kind of multiplication of various options is really something that needs to be tackled very soon, and the sector needs to, let's say, converge on some options. And that was one of the also ideas behind this analysis. The first thing that we looked at, obviously, was the cost of fuel production. And this, what you can see on this graph, the blue part shows you the cost of production of the hydrogen itself, that is basis of each of those fuels. And obviously, it costs the same no matter what fuel you then use. And then on top of that, the gray part shows you the additional costs that are needed to turn that hydrogen into the end state of the fuel. So for compressed hydrogen, it is just compression. For liquefied hydrogen, it's liquefaction, which is a bit more expensive and more energy consuming. But if you go to the synthetic fuels, then you get additional, fuel synthesis. You need to synthesize ammonia in a Haber-Bosch synthesis, for example. For LNG, you have to synthesize, you have to first capture the CO2, then you have to synthesize it with the hydrogen to produce methane, and then you have to liquefy it on top of that. So you obviously see that some options are much more capital intensive and would obviously always cost more than the pure hydrogen options. And that's one of the key, let's say, observations here. It's not a, let's say, groundbreaking one, that the less operations you need to do, the cheaper the fuel will be. But it is also important one to keep in mind that no matter also what assumptions you take about how much renewable energy will cost in the future, whether costs will continue to fall down or not, this kind of ranking will always be true, because the renewable energy and the renewable hydrogen will always cost. So the difference between those fuels and the fossil option will obviously change, but the relative ranking of those various fuels will always remain the same, and always the pure hydrogen options will be cheaper than the synthetic fuels. And another observation is that out of the synthetic fuels, ammonia is always going to be cheaper than the other more complex options, because it does not require a carbon molecule, which is an expensive one to get, to be honest. Especially if you assume some kind of sustainable way of capturing via direct air capture, for example, which is also quite energy intensive. So those are the two basic observations. The less simple, let's say, the fuel, the less its cost will be always, and the ammonia is the cheapest option out of all the synthetic fuels. Of course, there are other dimensions to the whole equation, and the other is the energy density of those various fuels. And here you can see that the ranking of those various options is exact opposite of the cost of producing of those fuels. So now the ones that were the cheapest have the lowest energy density and would require the most space on board of a ship. So compressed hydrogen would require 5 times more space than liquid hydrogen, for example, and liquid hydrogen will require twice as much space or even more than liquid LNG, for example, for the same energy content. And this, of course, has an impact on the, let's say, the business model of the ships, because not only will the ship storage system cost more, but at some point it will negatively also impact the revenue generating capacity of those ships. I mean, if you need to limit the amount of storage capacity, limit the amount of containers that you can carry because you need more space for fuel, that would of course have an impact on the whole business model. And we obviously also looked at that, not only at costs themselves. We also looked at other things than just the energy density of fuels. We also obviously consider the various equipment that would be needed to crack those fuels on board of a ship. We looked at the space required for the boil of gas, for example. We also looked into what would be the relative difference in terms of space required for a fuel cell versus combustion engine. So this was all taken into account. And this is what we basically saw when you combine those all those aspects into monetary terms. So looking at costs and also the value of lost revenues because of the additional space required for a fuel. The ranking is more or less, I mean, similar to the one that I showed on the energy density. But what's important here is that although the ranking remains the same, so some options are always most expensive than others, no matter what ship type you look at. When you look at ships that can be refueled more often, when you look at ships that can be refueled more often or don't require as much energy on board because the power requirements are just lower than maybe for some other applications, versus, let's say, deep sea shipping applications, you see that even though the relative ranking of those options is always the same, for those smaller ships, even though the most expensive options become much more manageable, let's say, because I mean, even though it's the most expensive one, the additional cost that you actually need to pay is a lot smaller than if you look at deep sea shipping, where those additional costs become prohibitive and just make those applications impossible to implement. Last part of the equation is obviously the energy conversion, so either an engine or a fuel cell. And I don't want to go into details because I mean, but just want to mention two aspects. So first, when it comes to fuel cells, generally they're a bit more energy efficient than combustion engines. So especially in maybe for lower power ranges where the engine has an efficiency of, let's say, 40% or 45%, and a fuel cell can have an efficiency of around 55%. So that's somewhat of an improvement and kind of lessens the additional space that we need for fuel. Then also for some ships that are powered by diesel electric setups that you produce electricity directly from a fuel cell, you don't need let's say a genset additional, so that also gives you some savings. Although on the other hand, where you need this shaft power and mechanical power, then an engine has an advantage, because for a fuel cell you then need an electric motor on top of that. But there is also another nice thing to notice here is that there is a difference in terms of the power to efficiency curve for a combustion engine and a fuel cell. Combustion engine, when you reduce the load of the engine below 80% to 60, 40, 50%, the efficiency drops substantially. And that's not the case for a fuel cell. So fuel cell can operate even at 20% of load, and the efficiency there is even higher than at full load. The optimum is around 40% of partial load, when the efficiency can go up to 60%. And this is also an important consideration when you start to consider the operational profile of a ship, because for some applications the average utilization of the power system is usually well below 100% or 80%, or it's closer to 60%. And then when you combine all those aspects together, what you can see is that there is just one of let's say a dynamic development there, that when you go from the less energy dense options to the more energy dense options, the cost of the fuel always let's say increases along that line. But obviously, as the energy density also increases, the impact on the storage costs decreases along the same line. So there is always this kind of trade-off that works differently for various ship types. And we have done this analysis for over 60 different ship types, and here you can see the results. And the results are that indeed, there is place for hydrogen, as we can see in the maritime sector. And what we did see is that for those short sea applications, where you can refuel often, even for some larger ships like ferries, and you can see this with the recently announced DFDS ferry between Oslo and Copenhagen, which is planned to run on compressed hydrogen. That even for large ships, this can work if you can refuel them very often. Then for the deep sea shipping applications, it's always synthetic fuels that prevail and are the most cost optimal option. And out of those synthetic fuels, as I mentioned, it's always ammonia that comes out of top. So for no ship type did we find out that the more, let's say, complex options like liquefied hydrogen and liquefied methane, so liquefied natural gas, synthetic methanol, synthetic diesel would be the optimal option. And then there is a big chunk of the market in between those two extremes, where liquid hydrogen seems to be the kind of the best out of those two worlds and give let's say the best combination of cost versus energy density. But if you look at the actual share of the market, so those various ship types have on the market and how much fuel they use, actually around 90% of the whole fuel consumption today would fall to the ammonia option. So even though that only for the, let's say, the larger ships and the deep sea ship application, because there are just so many of those ships and there's so much fuel, that would cover around 90% of the market. Then around 9% would be liquefied hydrogen, and 1% for those short sea shipping applications would be compressed hydrogen. And then the last thing that we looked at in our analysis was to see how much would that cost, basically, in terms of CO2 abatement. So as you well know, that there is currently ongoing discussion about inclusion of the maritime sector in the ETS system, where the current price of CO2 emissions is around 40 euros per ton of CO2, which is forecasted to grow also maybe around 50 euros per ton around 2030. Although maybe it will be higher, but I mean, those are the expectations. And as you can see on this graph, this will be nowhere near enough to make the ship owners go for those zero emission options, because the break-even point for a fuel switch starts at 100 euros per ton, and for some ships it is as high as 250 euros per ton of CO2. So as you can see, I mean, this is not to say that the ETS is a wrong option or anything of that sort, but clearly it will not be enough. So ETS alone will not make any change in terms of ship owners' behavior, or at least not a substantial one. And yeah, basically that would be it. I mean, it might look scary when you look at the cost, the additional cost. But what we also did was look at how much would the actual cost of cargo, let's say, transportation increase versus using the fuel options. And when we look at, for example, that a single cell phone transported in container ships between China and Europe, I mean, the price of that would grow by a couple of dozens of cents per one mobile phone. So while the cost of for the ship owner are quite high, it would certainly not also ruin the economy in any way, provided there is a level playing field, and the European ship owners are subject to the same, let's say, strict regulations that the competitors are as well. So yeah, that would be it from my side. Thank you very much for attention. If there are any questions, I'm happy to answer them.
Well, thank you, Mr. Pawelec, for your presentation, for a very comprehensive one with a good introduction of hydrogen, and we learned quite a lot about Hydrogen Europe as well. As we are quite good on time, I've got a short question. Will hydrogen be the next fuel? Will be the fuel of the future?
Yeah, well, I certainly hope so, but what we see is that it might play a big role in Europe for the intra-EU operations. But when you look at global shipping, then it becomes clear that it needs to be let's say a global consensus somewhere, because I mean you cannot think that the fuels will use whatever synthetic fuel at the end will prevail and tank it just in Europe, and I mean China will go for some other option and USA will go for some other option. It needs to be a bit more coherent. And then, if it does indeed go this way, we see that for deep sea shipping application, indeed, hydrogen might have a difficult time, because it's just this energy density of it is I mean half that of those synthetic fuels. So the impact on the storage capacity is quite significant. But to be honest, I mean we don't really mind that. I mean all those synthetic options in the end would require renewable hydrogen anyway. For their production. So from that point of view, we are perfectly happy to support whatever fuel is chosen by the industry. But I mean, what we just say is that the industry should hurry up and make the choice as soon as possible, because even though the targets are set for 2050, given the fact that the ships are in operation for 20-30 years, actually the change needs to start soon.
I see. Thank you for your comments and for your presentation.